Thanks a lot for the invitation. It's a nice place here, and also I enjoyed a lot, especially the discussions on this workshop. I know that you expected something about supersymmetric theories, I think, so I'm sorry to disappoint you. I'm going to talk this time about a much smaller project, even a tiny project in comparison to G-2 or something like that. So this is about lattice simulations on T2 cross R2, so on a twisted torus. And I want in particular to discuss a little bit the relation to confinement, and then also how to connect it to the confinement on R4. This work has been done in collaboration with Antonio González Arroyo. He in fact gave some years ago some related talks, and also my PhD student Ivan Sola-Calero, who's now a postdoc in Pisa. And yeah, most of it is in this article already, but I will also add some additional plots here, which are kind of preliminary, but I hope we will soon get some publication as well. So I'm very glad that Yuya basically introduced a lot of the theory part already. So that's why I can spend some more time to just show simulations results or to put some pictures of what he has explained, and also then to extend what he has done, basically, because he is in the very semi-classical regime, in the small T2 regime, and I will try to show how one can go a little bit further based on numerical simulations on this kind of setup. But to start with some maybe some illustrative appetizer, I will just show you how the topological charge density on this T2 cross R2 looks like. So this is simulation time, and here you see how how the topological charge evolves here. And I find it really fascinating what kind of different regimes you can observe with Yang-Mills theory. So this seems to be kind of a regime where you have a kind of Yang-Mills chemistry. So you have little particles moving around and then interacting with each other. So these are particle and antiparticles, so to say. So and to put it. Sorry? Sorry?
It looks more like biology.
Yeah, I mean, I slowed it down too much. So, yeah, to compare this a little bit based on this picture with what Yuya has talked about. So in his picture, these would be point particles, which are basically non-interacting, like noble gases or something. So here you see that there seem to be some kind of interactions and a little bit more than this idealized. Yes, basically these are fractional instantones, and the purple ones here are anti-instantones. So they are. See them meeting each other. Sometimes you see something getting out of the scale. This is when an instantone is built here. So but this, I will come to that. Okay. I cannot convert it by. It's pretty weakly coupled. Yeah, we will see later what kind of regimes we are in. So, but.
So in this simulation, you say when they make an instanton.
Yeah.
Because it's removed.
Why it is removed, I will come to that later. This is has to do with the lattice here. Okay, but just to talk a little bit about the general idea behind all of these approaches. So the general idea is basically that you introduce a small dimension of the space and you shrink the space so much that you reach the scale of the lambda QCD, so the confinement scale. And this additional scale helps you to get to a controlled semi-classical limit where the theory gets kind of weakly coupled. But what you want to avoid is any kind of phase transition on the way there. So you want to have somehow a continuous deformation. And I think that one of the cleanest ways to see this is in case of the compactification of supersymmetric Young-Mills theory. This is in fact something I worked on with Mithat Ünsal some time ago, but it turns out that this is rather complicated on the lattice, and it is especially difficult because if you study these kind of things on the lattice, you have to make sure that you are in the right regime concerning couplings, concerning lattice spacing, etc. And with super Young-Mills, you put on top of this the supersymmetry breaking and the fermion mass, so it's very difficult. So I always wanted to study something simpler first, which can be more easily simulated on the lattice. And therefore, I was glad to team up with Antonio Gonzalez Arroyo. And we first studied a little bit T3 cross R, so twist in all directions except one. But this has been studied also a lot by people in the audience as well. And therefore, I'm now concentrating here on this T2 cross R2. So this means you have also two large directions, and you can talk about string tension and Wilson loops in a much better way, which you can compare then also with Young-Mills theory in 4 dimensions. The whole idea is also related to something which Pierre van Baal put forward a long time ago, which is compare lattice data and analytic results and find regimes where you can match this to each other. And in fact, it has a very long history. So the names which were put forward in relation to what I'm going to talk about are kind of the quasi-particles and also the femto-universe. The earliest ideas with the name femto-universe were put forward by Toft, and then also Lüscher did a lot of works on this. And this was basically to use a periodic box, put QCD in a periodic box, shrink it so much that you can do semi-classical analysis, and then from there try to get towards the large volume regime and look at the states, the glue ball states, etc. This has a lot of problems, technical difficulties, which are related to center symmetry breaking in this setup. But later on it was realized, and Antonio Gonzalez Arroyo and others have put forward these ideas, that with twisted boundary conditions you can get much cleaner results, and you can achieve in a much cleaner way this kind of setup, calculations in the femto universe, and then getting the full theory from that. The other idea that it's also related to is the semi-classics, and there was always the idea of instantons, and later the colorons were found, and then also Maga basically worked on this as well. It was realized that you can decompose them into smaller bits in certain limits, these colorons especially, and this brings you towards a better understanding, especially if you want to compute confinement. And there has been some very new interests. Etsuko has worked on this as well, on T3 cross R, and then also in the ideas of new symmetries. This has been investigated much more recently. I put here just some ideas where it's related to, so you have certain ways to try to understand confinement, which are vortices and monopoles, for example, which need some kind of gauge fixing, which you can avoid if you study this, these kind of objects that are dominating on T2 cross R2. And then this it's also related to many other semi-classical approaches. And if you want to define some semi-classical contributions in the large n limit, then you are also led to these kind of fractional objects. So I just want to briefly mention the instantons as the first, these kind of quasi-particle semi-classical contributions that people have studied. Basically because I later on need also these formulas. I want to consider later on not what is typical considered, but I want to consider integrated topological charge density for this object, and this has this form here. Usually you have it symmetric in each direction, but it turns out that on the lattice, if you have fluctuations or small perturbations, it's actually good to study this also with a kind of anisotropy that can be introduced here, which was put forward in this paper. And basically the two parameters that you have is the radius, and then you have the topological charge of the object. And this is, and of course the location of the object. That is all you need to look at these kind of solutions. And in particular, there's a particular relation between the topological charge and the radius, which we will later use to find these objects also in lattice simulations. I'm discussing here mainly SU2. Maybe later on, so I have only backup slides for larger n. So the second idea is, which I mentioned briefly only because you guys talked about this a lot, is twisted boundary conditions. Basically, you can define some kind of periodicity of the gauge field up to gauge transformation, and then you have some consistency conditions if you move around one or the other direction of the torus, and this defines you, and this leaves only some kind of additional twist matrices which you can introduce for adjoint fields. Yuya has generalized this a little bit towards also including fermion fields with some specific constructions. So what we will discuss in the end is that this kind of twist is only introduced in the 0-1 plane. So this is this small t2 directions, and then we will study the theory on the R2 on the larger sizes. And yeah, the main thing is that this leads to fractional topological charge that can appear. If we twist only in one of these directions, we will still have integer topological charge only, but you will see that it still affects the contributions that you observe there. And the way you can look at this kind of fractionalization of the semi-classical contributions, basically you get in the small T2 regime, you get this Q equals 1 over NC contributions as dominating contributions. As if you look at the situation where you have twist in both directions, and this leads to these kind of, depending then on what kind of twist you introduce in the other direction, leads to this fractional solutions. And now you can extend these larger directions until eventually the twist won't play a role, and you will see that basically it will be populated by these kind of fractional objects if you keep the other planes small. The disadvantage of compared to the instanton, if you look at these contributions, if you investigate them, is that there is no general analytic formulas for this. They are found numerically on the lattice. There are also certain situations where you can provide results, but analytic results, and there are also expansion regimes. Eric Poppets, for example, has worked a lot on that, and also, of course, Marga. But in general, you have only numerical results. And these depend, basically, the scale of these objects is given by the scale of the small circle, of the small torus, which is this LS scale. In both of these torus directions, it's the same size. The advantage of these are that they are, in contrast to the instanton, they are much more localized. So you have an exponential suppression of the radius, if you go to larger and larger radius. Now, this has been, these kind of observations have led to a proposal of a fractional instanton liquid model. So these fractional instantons seem to be kind of the most elementary building blocks, and they also, because they are kind of vortex-like contributions, they can, in contrast to instantons, lead to an explanation for a microscopic explanation for the confinement mechanism. In the advantage compared to vortices is that you don't need any kind of gauge fixing, and it's a liquid model because only if you shrink this this T2 torus, the torus with the twist, very small, you will have a dilute gas of these objects. But if you then go towards the full R4 theory, you will get a higher and higher density, and then at a certain point, according to this proposal, the size is not anymore given by the size of the T2 torus, but instead of by the scale of the strong force by lambda QCD. The proposal for the confinement mechanism in this approach is based on the dilute abelian vortex approximation. So you assume, at least for this small T2 regime, you assume that they are independently distributed, and each of these vortices contributes to the area law inside a Wilson loop on this R2 plane. And this leads to the fact that finally you have a string tension which is proportional to the density of this fractional objects. And in more detail, it should be 2 times the density. Now, this assumes that this vortex is infinitely thin, but actually it has a finite radius. And here you see some deviation of the string tension if you consider smaller and smaller Wilson loops around a single of these fractional instantons. And the interesting thing is that you basically, first you start this is a deviation from this result of 2. So you start at 0, and but then you have a region where it also overshoots a little bit. And then it approaches this finally, for very large Wilson loops around this, it looks like a point-like object. Okay, now we want to use Monte Carlo to study this kind of proposal and want to investigate how much it is realized in the Monte Carlo data. Therefore, we need to identify the semi-classical contributions. That means also we have to filter out some of the ultraviolet noise, which is dominated by lattice artifacts, and then we have to identify the semi-classical objects. We are mainly using SU2, Yang-Mills theory, with a large number of different lattice sizes, and also varying beta to have a decent amount of coverage for the lattice spacing. For this kind of ultraviolet filtering, we are using the gradient flow method. Yeah, and this is just if you look at the string tension as a function of this small T2 size, you will already see that basically you have an increasing function until it finally reaches at a certain point the infinite volume result for the string tension. No, on the x-axis, this is a femtometer. So it's if you assume that for SU2 you have the same scales for the string tension as yeah, Fermi.
So is that true that pretty much one or that looks one?
No, this is not one. It's one. It's sigma over sigma 0, and sigma 0 is the. So yeah, yeah. So it.
But I was trying to connect that. If I recall correctly, an average instanton, as I did use, of 0.3 Fermi. So diameter 0.6 Fermi. So it seems that when the average instanton is just starting to push the co-amplify dimension, that's when you.
Well.
That's when you really go to the.
Well, the dominant things, the dominant semi-classical objects are not instantons here. So they become more and more dense, and we will see what is happening. But instantons also play a role in this.
It's fine. I just didn't know whether it was lattice unit or physical.
Yeah, I always try to convert to physical units here. Yeah. Okay, just one short comment about this gradient flow. So it is done basically a kind of smearing, which is it's compatible with the cooling method, where you try to find a minimum at the action. It basically drives you towards saddle points of the action, and it's always given in terms of a certain lattice action, but it has some limitations in our investigations. One of them is that you get, whatever you try, you get always pair annihilation if you let this continue. Of course, you want to have pair annihilation as long as it's just noise, what you annihilate. But then you get also some annihilation, and this is, if you look at the energy in units of the flow time, you see the steps here, and these are kind of always some kind of pair annihilations, and this happens for all kind of flows because it's like a physical effect. If you average over a certain density, over a certain distance, then you will always tend to annihilate these objects. What in addition appears is that you get, for certain lattice formulations, also annihilations of instantons. And this has to do with the deformations that you do with these kind of flows, gradient flows, and it depends strongly on the action. So some of them tend to shrink these objects until they basically fall through the lattice and cannot no longer be resolved. Yeah. Okay. I have to speed up a bit. So the next step, now we have these kind of distributions of averaged fields, which look like the plot down above here. Now we try to find peaks in these kind of distributions. And these are basically defined in the most simple way by just looking at the highest point compared to nearest neighbors, and then we are doing a fit around these maxima. What we are using is, in fact, for all of these fits, we are using the instanton profile, because there's actually not so much difference in this very short distance regime. If you go further out, there's a large difference, because you have the exponential decay with the distance only for this fractional instantons. But if you consider short distances, this is a decent way to do it. And the fitting parameters are basically these rho parameters, which are kind of a little bit anisotropic extensions, radii of the instanton or the peak, and then also the maximum of the peak. I cannot, at this point, I cannot distinguish. But let's have a look how they look like. Oh, I hope one can see this. The good thing is, if you look at the distribution that you get from just looking at the peaks on the configurations after the gradient flow. So this is just taking the topological charge density and then looking at these peaks. You will recognize that basically in the histogram, you have a huge contribution which is very narrow and which comes from this single point here. But then you have also some other features around it. Now, you can compare this to the predictions, and if you compare this to the numerical generated solution for the fractional instantons, you will see that this peak basically coincides with this value that you have for this maximum. So this is very good. So basically everything here is a fractional instanton. If you go to this, this is in the small circle regime, small T2 regime. But then you have other contributions, and I've drawn here some lines which correspond to instantons with Q equals 1/2, which is quite close actually to the peak that we observe here in this fractional instantons, and then also Q equals to 1. Now, this additional feature that you see above here is basically not really on top of this line for the instantons. Therefore, it's not really clear what this belongs to. But if you look at lattice deformation of the instantons, then you will see that it basically agrees with this. So on the one side, you have basically lattice artifacts because you have finite lattice size, which lead to this deviation, and eventually the ending point here is where the instanton basically cannot be resolved by the lattice anymore. And on the other side, you will see, because of this small T2 direction, the instanton will feel the finite directions in the other sizes until it dissolves basically in this fractionals. But then there are also further additional features which are this band down here and this other band, and to resolve these, you have to separate then the peaks which are well separated, and this is a plot up there where you see that you basically only see fractional instantons and instantons, and then you have the peaks which are closer to each other with the same sign, which are above there, which lead to a distortion, which basically is due to overlapping peaks. And then you have this band down here, which are peaks with the opposite sign. And this is basically what is generated also during the flow by pair annihilation. So you get this kind of additional peaks which are down here, which are basically pairs which get annihilated. So you have a kind of easy understanding of all the structures in these diagrams. Now you can have a look, try to have a look to get a more quantitative picture. And basically, if you plot everything that we got, you have it's shown in the plot up there. But at a certain point, you have to make a cut here because you no longer are in the semi-classical regime, and in particular, you get some objects which have a non-trivial T2 dependence. And then you have also some of the plots which have quite coarse lattice spacing because the beta value is rather small. And this leads to problems of separating noise and signal. And therefore, we have to discard them as well. And then you have also points which are where you have only 4 lattice points in this small T2 directions. And these lead to a poor resolution of this fractional profile in this small direction. And therefore, you have to remove them as well. And then you end up with this kind of plot here. This is basically this separating out only the fractionals this fractional instantons, then you get these kind of plots which show a rising with this small direction, and then a saturation about 0.7 Fermi. Okay, now I have to skip this. It's basically you can compare also with some more quantitative investigations of the densities, some predictions which come from the semi-classical analysis, which is basically a suppression with the fractional instanton actions that you would expect here, and this fits very nice to the expected formulas. Now you can also compare the string tension, and if you compare this with the density of this fractional instantons and anti-instantons, the interesting observation is that on this scale, it's actually quite close to the expected thin abelian vortex approximation for the whole range of investigated sizes. It is, but however, it's consistently a little bit above it. So you get somehow, due to the finite size of these vortices, you get some additional contribution to the string tension, which increases it a bit. Now, if you, the title of the talk was to confinement. So what happens if you go towards R4 and you increase the size of this small torus? Then what happens is basically the density of this object grows, and also the radius. So here this rho Fi is not the density, but instead it's the radius of the object itself, until basically the density, the distance between the objects becomes comparable to their size. And there basically you are at the edge of this semi-classical regime. And this dilute gas approximation does no longer work. So if you want to investigate this limit, also in terms of these densities, you have to do actually fits which include also this a non-trivial dependence on the T2 directions, because when these directions become larger and larger, this plays a very important role. And you can see here how this small circle regime approaches then larger and larger circles until you reach some size of this T2 plane, which is basically compatible with the large volume results which I put here. So the complete density of these objects becomes then comparable. So I think I have to stop now. What I've shown is basically how the semi-classical regime that was also introduced in Yuya's talk is reproduced on the lattice, how the area law is indeed generated in this thin vortex approximation, but there are some additional corrections. Then you can resolve with this also different kinds of semi-classical contributions. And the numerical data have the big advantage that you can basically continue from the semi-classical regime to the large volume limit to the full Young's theory. This shows that you have a saturation of the density at around 0.7 Fermi, and then at that point the distance between the objects becomes compatible with their radius, and this is where you basically go from a gas approximation to this liquid, this fractional instanton liquid, where you where the sizes of these objects is given by the density and no longer by this T2 torus that we added. Thanks a lot.
Thanks very much.
In this picture, do you imagine that, since you're putting in real numbers, that when you get to where the density is of order 1, when they begin to overlap, that defines lambda QCD? That will turn out to be? I mean, you haven't, obviously.
Well,
not order of magnitude, but...
yeah, it defines a certain scale in that way, yeah.
And
yeah.
that scale compared to lambda QCD, what do you think it would be? 2, 1, 10?
I think so. I think there are estimates based on that that also Antonio proposed, put forward in his proposal of this fractional liquid model, where you basically estimated from these kind of turnover. Yeah, but I'm not 100% sure about how to do this in a more in a proper way. Yeah, I mean it's 0.7 Fermi, so yeah, but it's kind.
Yeah, I know, but the question is, from a theoretical point of view, is there any argument that you would sort of...
No, the problem is that...
what?
It's a fact, there is no analytic argument. This is SU2, and all the numbers refer to SU3.
Yeah, but we fixed the string tension with the same conventions as in SU3, so yeah. Yeah, okay, that's true. Yeah.
Okay, next question, Claudia.
I wanted to ask you if you plan to compute features of the topological charge distribution, because, for instance, if you could compute the kurtosis of the distribution, so the ratio between the connected for expectation value of q to the 4 divided by q squared, there is an exact prediction from the dilute gas of fractional instantons. And recently we have shown that in our setup with the long side, which is n times the short size, the matching is uncanny. And also some years ago I computed in the large volume limit this quantity as a function of m, and it matches the fractional dilute instanton gas prediction apart from a factor of 2, which I think fits very well the instanton liquid, the fractional instanton liquid prediction. So I think it would be interesting to compute this quantity.
Yeah, I mean we definitely want to have a look at the topological susceptibility and of course any kind of other quantity related to that. Yeah, there are predictions for that and also relations between this and the string tension. So yeah, we want, this is what we are basically currently doing, but yeah.
Yeah, but the fact is that we know that the topological susceptibility is not very well described by perturbation around 1 instanton. So typically what we do is to fix it from the lattice result and then compare the next order moment of the distribution. This is why I was talking about q to the 4.
Okay, we can discuss it. It would be interesting. Yeah.
So can I have a question on the crossover of the size of the T2? So in the case of SU2, without having any, for example, adjoint fermion, can we smoothly connect small T2 to the alpha limit of confinement? Or
so you want, what do you mean by connect smoothly?
Yeah, so this is small T2 semi-classical confining regime. Is it connected to alpha?
Yes, I mean what you see in the string tension and in the other quantities I've shown, there is no transition. Basically, there's a continuous connection, which is also in spirit of this liquid model where you have basically not strong phase transitions, but, so a first order or something, a second order phase transition, but rather a crossover to this liquid. Yeah, we have discussed this already. This is a different regime.
So in gradient flow, so is a self-dual condition is satisfied in whole flow time region?
I have not investigated this. You mean if I look at the semi-classical contributions? Yeah. Yeah, this is fulfilled to very good precision, but yeah, I mean, you have seen that basically, how to say, if I go to very large flow times, I will destroy even instantons with the flow. If I use normal Wilson flow, it will shrink these instantons until they basically fall through the lattice. This has been investigated already a long time ago by using cooling. Marga has worked on this, but the same holds here as well. So for the gradient flow, this also appears. And then if you change the action, you can have basically even the opposite. So you can grow the instanton size. And here you can grow it. This is in fact how I generated these plots of the lattice instantons. You can grow it until they dissolve and this fractionals or some other weird shapes appear.
So it's a follow-up. I am confused. You are doing gradient flow, and then are you measuring the FF dual operator which measures the instantons? Or do you have an operator for the fractional?
No, this is it's just the topological charge density.
So can you tell whether you see an instanton or fractional charges?
Yeah, the only way I can distinguish them is if I do a fit, and then I see the relation between the radius and the maximum is different for a fractional and an instanton. And if I go to a dense regime, then this is hard to resolve because I have overlapping effects. Yeah. But in this dilute gas regime, I can easily resolve it, so distinguish the two from each other.
And do you know, I think you flew, if I read it correctly, you had flow times of in the hundreds?
No, this was for this example. So actually, I didn't put it here, but the flow times here was 15 for this beta 2.6, which is kind of, I think, 1.5 T0. So it's not.
So because the footprint of the flow is square root of 8 times the flow time, that is flow time. So if it's 15, that's about 120, the square root of it is like 11. So it means that you smear out to distance 11, which is much, much larger than your small distance. Does it matter? It might not, but
at this scale, so for these kind of contributions, it doesn't matter. They are really, I mean, I can, I don't have time, but I can show you pictures where you can flow up to 500, and still these fractional objects are stable. So these fractional instantons, which are kind of lumps in this, which are locally self-dual, and they are stable because they are kind of saddles. Yeah.
So you can say that the lumps are stable, and then you have to go there and decide whether
Yeah. Yeah, I mean, I can.
Can I just ask another question?
If you, this, I mean, this just shows, I just want to add, maybe, so this shows why we are doing the flow. This here is flow time 4, and then you see this pool lump, big shape here down here is basically the noise. And you want to separate this. And if you go flow more and more, then you see that it's moving downwards and until you reach this picture here. So this is basically why we are using this flow. And these objects are very stable under the flow.
So it's not the launch yesterday, this picture. Has anyone done like the theory, the supersymmetric, n equal 1 supersymmetric this way? Yang-Mills?
The idea would be to, you mean n equals 1 super Yang-Mills theory?
Yeah.
The idea would be, of course, to do a similar analysis there. But as I said in the beginning, I wanted to have first something where I can find the scales and test the methods where it's easy to...
No, I understand, but I mean, what if there is some surprise?
Yes, there are some interesting questions. For example, the regime for supersymmetric Yang-Mills theory is this S1 cross R3, and then you can try to find connections between the two regimes. There are analytic works. Yuya has worked on this. Yeah, so this would be interesting, but it's much more expensive.
So, just before you end, could you go back to the movie and explain what's happening?
Okay. So basically what you can see here is that certain instantons form, and if they are very large in height and have a small radius, then the flow tends to push them through the lattice. And this is what is happening here, basically. I mean, in some cases, they even dissolve afterwards. So I think there's also a continuous way of having these objects merging and then getting away from. Yes, this is simulation time. Yes. Yes, basically this is simulation time. I had to engineer this a little bit. So this is the largest beta, which slows down the topological oscillations a bit, and then I had to slow down also the.
I hate to break this up, but we're a bit over time, and so I think let's thank Georg again.